Hello everyone, this is another video on the book Introduction to Probability by Blitzstein and Huang, second edition. You can download the book freely and make good use of it, which is great. In this section, we are going to talk about a non-naive definition of probability. Previously, there was a naive definition of probability where you could imagine that you had a certain finite number of little objects that were all the same size, and you didn't have to worry about some of the things we'll have to worry about now. To apply probability with enough generality, we need to have events that are not all equally probable. Now recall that our sample space is the collection of all the things that could possibly happen. We call that S. Now we want to have a function which goes from some arbitrary subset, that is, you get to pick it, from a subset, any subset, generally, of S to a real number. Well, in some cases, maybe not just any subset, but in many cases, it'll be any subset. Any nice subset. So A might be the empty set, which will be kind of boring, or A could be the sample space S. And in either of those cases, we'll get something extreme. The probability of the empty set is 0. It's certain that, it's certain that something will happen. There's no probability that nothing will happen. So P of the empty set equals 0 says there's no chance that nothing will happen. The probability of S equals 1 says it's certain that something will happen, basically. Okay, now let's suppose we have some disjoint events. That means they can't both happen. They have no overlap. Their intersection is empty, if you think in terms of sets. Now we can ask ourselves, what is the probability of the union of a bunch of events? So this one happens, or that one happens, or another one happens, or something along those lines. And it's quite easy in this case because they are disjoint. That means they cannot have more than one of them happen, which means there's no worry about double counting or triple counting or in general multiply counting places that are part of the intersection. So our probability will just be a sum of the probabilities of the individual sets. Now that would be true if we have a sum over up to 2 or up to 50 or up to any integer n, positive integer, or even if we have a sum up to infinity. So this probability axiom here is actually called countable additivity. It seems quite reasonable. It's perhaps even more clearly true if you say that it holds for finite n, but don't say about infinity. That's called finite additivity. Anyway, so this is our probability of unions when the sets are disjoint. Now we have some useful properties here. Recall the complement of A is everything that's in the sample space S that is not in A. And we can write this as A complement equals S, taking away everything that is in A, if that helps. Of course, you probably don't know what the right side means until you already know what the left side means. But anyway, it's something you could write down. Now, the probability that A does not happen is the probability of A complement here. The probability that A happens is the probability of A here. And you see the probability that A does not happen equals 1 minus the probability that A happens. And I think that seems very reasonable, but it seems perhaps even more reasonable if I add P of A to both sides. Then I see the probability that A doesn't happen plus the probability that A happens equals 1. And surely that's something that we would want. Okay, property 2, if A is a subset of B, then the probability of A is less than or equal to the probability of B. Now, a typical subset will be, in some intuitive sense, smaller. It'll leave some stuff out. I mean, smaller may not make a whole lot of sense, but it'll leave some stuff out. And if it leaves some stuff out, then maybe it'll leave out some probability also. Now, there are special cases, like if A is the empty set, then the probability of the empty set will be less than or equal to the probability of B, because after all, the probability of the empty set is 0, and that's as low as it gets. So this is less than or equal. In many interesting cases, it will be less, but maybe not in all of them. Now, this last property here, I think, is especially interesting. So let's suppose I have events A and B, and I want to know the probability that either A or B happens. And recall, we think of or in an inclusive sense. If I'm happy if A happens or B happens, or even if they both happen, then that gives me the union here. So the probability of this union will be, well, if A happens, then I win, or if B happens, then I win. But what happens if A and B are both true? Well, I only get to count them once in the union, but I count the intersection. I only count the intersection once over here, but I count it twice in here. So these aren't going to be equal unless I introduce this correction here to avoid double counting. So I can do two things here. One, I can draw a picture. So I haven't drawn my sample space, but I can have a rectangle that everything fits in. Beautiful rectangle. Well, maybe not. Anyway, I'll say it's a rectangle. Now I've got A and I've got B, and you will notice that they overlap in this region here. So the probability of A union B means I've got this area and I've got this area and I've got this area, but I only count this area once. And as we saw over here, I'll count it twice because I would get all of A and I get all of B. So to get it to work out, I will have to subtract by hand, so to speak, this region here. Now something else I can do that's a little bit fun is I can move the intersection term over to the left. Now, why would I want to do that? Well, one reason I would want to do that is to show that this formula is even easier to remember than you would think, because we have the intersection and the union appearing symmetrically, both of them with plus signs. That means you don't really have to try to remember which one's plus, which one's minus, because when you have the union and intersection on the same side, they're both plus. Now, how would we interpret this expression? Well, this says the probability of anything in this peanut-shaped blob plus a second helping of what's in this overlap region equals the probability of A, that's this more or less circular region here, plus the probability of B, that's this more or less circular region here. So I introduce the probability of the intersection here because I know that this intersection is going to be counted twice on this side. So I can see why this is true, and when I've done this, I see that these intersymmetrically, and so there's no minus sign that I have to work hard to remember. So I think that's a little bit fun. Okay, now this intersection union formula, in fact, generalizes if I have more than two sets, then we can call this, or it's worth calling this the inclusion-exclusion theorem. So now let's suppose I have n events, where of course they're typically not disjoint, or else there wouldn't be much to do here. So the probability, you might think, I can start by adding. So here is my set A, here is my set B, and here is my set C. And of course, this is all within the sample space F. Okay, well, if I want the probability of this kind of blob region, this whole thing here. Well, I can start by taking the probability of A, that's this circle, and the probability of B, that's this circle, but I already see I've got some overlap, so I'm going to have some correction to do. But I also need to add in the probability of C, but now I've got even more overlap, and I notice there's even a region that's in all three of the sets. So I'll start by adding the probabilities of the individual sets, but then I will have to take away some overcounting in order to get this all to work out properly. Now you see this expression sum over I as less than j. Now that's kind of a shorthand. What that means is I'm not going to write the sum and the thing that I'm summing, but what I can write is an expression that involved j and I. So I is supposed to be less than j, so I'll let j be my outermost summation, and it goes from 1 to n, the number of sets that I'm dealing with. I is, however, restricted. It's not I equals 1 to n as we typically see, but I has to be less than j. Well, the smallest I can be is 1, so I'll put that. But for my limit, if I is to be less than j, then I had better be at most j minus 1. So that is how I could cash out this expression here, sum of I less than j. Now I can do the same thing if I want to explore this sum over I less than j less than k, and this will be a little more complicated. Now let's have k be our outermost summation because it is not restricted. So it goes from 1 to n, but I need j to be less than k. Well, the smallest j can be is 1, but the largest it can be is what? K minus 1, right? And then I has to be smaller even than j. So I could write I equals 1 to what? J minus 1. Now let's suppose n equals 4 for the moment. Then I could have, for my triple intersections, I could have A1, A2, and A3, or A1, A2, and A4, or A1, A3, and A4, or A2, and A3, and A4. So this is how you would keep track of these things. And you'll notice we keep getting these sign flips because we're making a correction and then we overshoot. So we do all this addition and then we say, oh, we need to subtract the double counting. But then we notice, oh no, we've done too much because what about this triple intersection region? So we add some back in. But then if we've got a set, if we've got 4 sets intersecting, then we'll have to subtract off some more. Then if we've got 5, we'll have to add some more back in and so on. And so we'd get even more indices and so on. But the number of terms kind of grows in the middle and then it shrinks again near the end. So it doesn't just get worse and worse. Okay, so this is useful, or this can be nicely illustrated by a problem that's useful for solving, which is called the Montmort matching problem. So this was a card game, which was conveniently called 13 in French. And the reason for 13 will soon make sense when we see what sort of deck one would play this with. So suppose you have a well-shuffled deck of n cards, labeled 1 to n. Well, how can we get that with a standard deck? Well, you could interpret an ace as a 1 easily enough. It's only got 1 club on it, or whatever the suit is. And you could think of a jack as 11, queen is 12, king is 13, and there you go. Within one suit, you have a 13-card deck. So if you want to have n be larger than 13, then you will want to use a different deck, or maybe have some other way of counting these things. But it's very simple if you just pick one suit and say, ace up through king, hence 13. So if you want n to have some definite fixed number and make it be as big as it could be with a standard deck of cards, then you could think of n as 13. Of course, you could think of it as smaller and still use a standard deck, just throw away parts of it. If you want it larger, then you'll have to do something more clever. Anyway, well, what do? You flip the cards over one by one, and you say on your first card, 1, whatever the card is. It isn't necessarily an ace, but if it is, you win. Let's suppose it's not an ace, then you flip over a second card and you say 2. And the card isn't necessarily a 2, but if it is, you win. And you can probably see where this is going. If you haven't won yet, then you flip over a third card and say 3. And if it's a 3, you win. And so on. And you keep doing this until you get to your nth card, which might be 13, let's say. And if at some point you see in front of you a card with a label that matches the number you said, then you win. So what, de Montmort asks, is the probability of winning? Well, this is a fun problem for illustrating this inclusion-exclusion theorem, because basically everything about it that's interesting comes from these correction terms. You might think, after all, let's suppose we have A1 be the probability that you get an ace on your first number, and A2 will be the probability of getting a 2 on the second card, and so on. So the probability of winning, you might think, is the probability of A1 plus the probability of A2 plus the probability of A3 and so on, because you could win on the first card or the second card or the third card and so on. But a couple things happen. Well, one, the probability of your getting ace on the first on the first card is just 1 over n, right? Which could be 1 over 13, or maybe it's a different number. The probability of our getting a 2 on the second card would seem to be 1 over n. After all, these are all equally likely. The probability of getting a 3 on the third card would seem to be 1 over n. And we can add these up, and we'll get 1 over n. So we get n of these, and what do you know? Guaranteed to win. Is that right? Well, of course it's not right. You certainly could fail to win. Maybe you have a pretty good shot, but you have no guarantee. So what have we done incorrectly here? Well, we have failed to take into account the fact that there are decks that have, say, an ace in the first position, but also a 2 in the second position. Or maybe they have a 7 in the 7th position and a queen in the 12th position. And so if we just add all these, then we are double counting or triple counting. In other words, we are over counting. We are multiply counting things. And so we cannot simply use this formula here of all these. Instead, we will need to subtract our expressions like the probability of A1 intersection A2 and the probability of A1 intersection A3, and there will be a bunch of these minus probability of what? A1 intersection A13. Recall the 13 is the king. And then we can move up to the 2, and we'll have the probability of A2 intersection A3, and so on. So I have quite a few of these correction terms here, because 13 is a lot bigger than 2. But when I do all that, I will find that I have overcounted, and so I will have to add in the probability of A1 intersection A2 intersection A3, and a bunch of terms like this. So we have, let's see, n terms from our A1 or A2 or A3 expression, but we have here the probability, let's see, getting the ace on the first and a 2 on the second, well, that probability, the probability for one of these terms is what? 1 over n times n minus 1. We could write that as n minus 2 factorial over n factorial. So that's for one of these terms. But let's think about how many there are. Well, there are going to be, we want combinations, don't we? We have 13, 13 ranks, if you like, 13 numbers, and we're choosing 2 at a time. So we want n factorial over n minus 2 factorial 2 factorial. And conveniently enough, the n minus 1 here is just n factorial underneath and n minus 2 factorial above. And so we get a lot of cancellation. And what we keep is the 2 factorial. Now, if we do something similar for the 3, the intersection of the 3 sets, so that I've got 3 cards that match the order in which they have been exposed, then I will get a plus 1 over 3 factorial, because I'd have n1 or n minus 1 n minus 2 in the denominator, and then I would have n factorial over n minus 3 factorial 2 factorial, and again everything will cancel except this little factorial here. So I get a plus a 3 factorial, and then I'll get a, if necessary, a minus 4 factorial, and if n is bigger than 4, I have to keep going. This is, of course, 1 over 4 factorial. And then I'll need plus 1 over 5 factorial. Fortunately, factorials are pretty big, so 1 over factorials are pretty small. And you can see how this is going to converge, and then minus 1 over 6 factorial, and so on. Now, this will remind you, perhaps, of the exponential, the Taylor series for the exponential, but it isn't for a couple of reasons. One, this is the linear term, and this is the quadratic term, and so on, which means we've left off our 0th order term. And two, well, if we take the exponential of minus 1, then it almost works, except the signs are all wrong. So what we get is actually 1 minus 1 over e. It's 1 minus e to the minus 1. So if you write out the Taylor series expansion for e to the minus 1, then you flip the signs of all the terms, and then you add 1, so you cancel off the 0th order term. Then you get this expression here. And this actually can be evaluated, and it comes to approximately 0.63. Now, if you start with sufficiently small n, you can easily work this out, like if there are 2 cards, or if there are 3 cards, and so on. And you get a little bit of oscillation, but it converges, and this is what it converges to. So you'll notice the reason that this probability was something interesting, like 0.63 instead of 1, as we briefly feared it was when we were looking at this expression, is because of all of these correction terms and correction terms for correction terms and so on. So it's basically the inclusion-exclusion formula that does all the work here and keeping us from getting something other than our very naive answer of 1. And so that is a nice illustration of the inclusion-exclusion theorem in a case where we have a lot of symmetry. And this is important for enjoying using this formula. If these expressions are all equal to each other, because A1 and A1 intersection A2 is just as probable as A1 intersection A3 and so on. If that's true, then I only have to count these up, and that'll give me a nice combinations formula. And then if I know the probability of any one of them, then I can work it out nicely. So symmetry is what makes this fun. Without symmetry, it is noticeably less fun, though there are still some cool problems that you can do where the symmetry is not as straightforward as this. Okay, so we have illustrated the inclusion-exclusion formula and seen how it gives us the answer to de Montfort's matching problem. And if you're so inclined, you could take a deck of cards and do this. And after sufficiently many tries, it could get a little tedious, but anyway, after sufficiently many tries, you should find that your relative frequency is reasonably close to 0.63. Which leads to one other issue I want to say something briefly about. We talked about axioms for probability, but we didn't say what probability means. Now, you may wonder, what does it mean to ask what does probability mean? Well, there are some things, the world is only given once. And so, maybe I'm a juror and I have to decide, do I think that the defendant is guilty? Well, this isn't an experiment that I get to run a whole bunch of times with similar, similar evidence and similar defendants and so on. And flip back to the answer key, which of course I don't have, but if I did, maybe I would be able to say, well, M over N of these criminals were guilty. Well, of course, life is not like that. We don't get trials over and over. Now, if you're a Bayesian, you think probabilities are degrees of belief. And you can have degrees of belief even for, individual events that are not repeating. Now, whether degrees of belief are well-founded, well, that is a good question, and there are various things you can say about that. On the other hand, in some cases, there will be some that won't, probably. Now, if you have relative frequencies, many Bayesians would say you should pay attention to them, but if you don't, you can still have opinions. Likewise, if there are symmetries, you may pay attention to those, but in the absence of those, you can still have opinions. On the other hand, frequentists are very strict about probabilities, and they will say these only make sense when they are relative frequencies. So we've got a sample of, we've got a large number of instances that we get to sample from. So frequentists would say you shouldn't pretend to think probabilistically where you actually can't. The Bayesian will say, well, yeah, you can't always get what you want. Life is hard, but it's better to do your best than to give up and do nothing, or use, or to leave resources on the table, so to speak. We could have reasonable opinions which are better than, whatever the alternative might be. So there we are. We've looked at some properties of probability, and in particular how we calculate the probability of a union of sets when the sets are overlapping rather than disjoint.